Okay, so this is going to be one of the longest lectures you're ever gonna get in either honors or AP chemistry, and it is the infamous titrations unit. There's just going to be a lot. You have to really visualize what's happening in each step of the process, and I'm going to be trying to diagram whenever possible what is happening, but you really need to make sure that you pause the video as often as you need to really absorb what I'm talking about. And we're going to be going into much more detail with the long titration protocol that goes along with this. So the first thing we should know is what exactly is a titration. And it is a neutralization reaction between an acid and a base. So we may, for example, you have a acid, could be strong or weak, and then you add a strong base to it, specifically hydroxide component, and it's going to form water and the conjugate base in this one example. Okay. So in the case of this, we have a Erlenmeyer flask with an acid of an unknown concentration. And this is the HA in here. And then this solution, which we don't know whose molarity, we don't know, is called the analyte. And then you have your burette above it, and that is filled with the OH minus, which in this case would be the titrant. And you know the molarity of the titrant, so we keep adding drops of the titrant to the analyte until we see a color change using what you call an indicator that will change color when the equivalence point has been reached. And the equivalence point is the point where equal moles of acid and base have reacted with one another. Okay, we're going to be doing some of these again in lab. We did this lab already earlier with the acid-base thing, but I really want to once again emphasize the terminology that's used right here. So the first thing we're going to do is we're going to talk about adding a strong acid to a strong base, or adding a strong base to a strong acid. Okay, now it's very, very important to remember that strong acid have negligible conjugate bases, and vice versa. A strong base has a negligible conjugate acid. Okay, so in this case, we are going to look at a calculation involving the titration of a strong acid with a strong base. Okay, HCl is a strong acid, so it's going to have a very negligible conjugate base, the Cl- ion. So what we need to do is we need to calculate the pH when you first have HCl. Okay, so we have a beaker, and or in the case, it could be an Erlenmeyer flask, whichever one you want to use, and it's got HCl in it. And it's very good to think about what is happening here. We have H plus ions and Cl minus ions. And because it's a strong acid, we can assume that the H3O plus concentration equals 1 molar. Therefore, the pH before you've added any of the base is going to be negative log of 1. Okay, and then that will give you a pH of 0. Okay, and that indicates that you have a fairly high concentration of a strong acid. So the pH of just this is 0. Okay, now we're going to look at what happens when you add 10 milliliters of the 1 molar NaOH. Okay, so the best thing to do is to first start off with a net ionic equation for what's happening here. Okay, the complete ionic equation is HCl aqueous plus NaOH aqueous to give you NaCl, which is soluble, and water. Okay, but as you know, you can break up strong acid completely in an anionic equation. I'm going to cross out the Cl and the Na because they'll both be aqueous. So the net ionic equation for a strong acid and a strong base is H plus Aq plus OH minus aqueous gives you H2O. And we don't really care about the amount of H2O, okay, because that will not have any kind of an effect on the pH since water is neutral. I'm going to cross off this one. Okay. Now we have a combination of a strong acid and a strong base, and we need to figure out how many moles of each are left over in the end. So what I'm going to do is I'm going to do it before reaction. I'm not going to do a change line this time because it's all 1-to-1 after the reaction. And then I like to also have a line to calculate what the molarity is at a given moment. Okay, so we're going to figure out how many moles of the H plus and how many moles of the NaOH we have. So we have 10 milliliters. That's going to be 0.01 liters times 1. So this is going to be 0.01 mole of the OH minus. And earlier, we had 40 milliliters of 1 molar hydrochloric acid. So that's going to be 0.04 mole. Okay. Now, after the reaction, because OH minus is limiting, you have 0 moles of this. You're going to have 0.03 moles of this. But in order to be able to use any kind of pH formula, you have to have the quantities expressed in molarity. Okay, because the pH equals negative log of the H plus. Okay, so the H plus moles is 0.03 moles. However, the molarity is actually including a final volume of 50 milliliters. Okay, 10 milliliters plus 40 milliliters of the actual other one here. Okay, so 0.03 divided by 0.05 gives you a molarity of 0.6 for the H plus. So then the pH would equal negative log of 0.6. And that gives you a pH of roughly 0.22. Okay. And if you think about what's happening here, so we can look at the beaker once more, and it had H plus and Cl minus, but it's also going to have at this point some Na plus, okay, because those were spectator ion. However, you're not going to have any OH minus because they react with the H plus, and the H plus is going to be left over. So at this point, the beaker looks more or less like this. Okay, remember that Cl minus has no effect on the pH because it is a negligible conjugate base, whereas Na plus also has no effect on the pH because it is a group 1 element. It's the cation of a strong base, NaOH. Okay, so at this point, the pH is still very low because you have only H plus that has any impact on the pH. Okay. All right, so go ahead and take a moment to set up your own before reaction, after reaction. So pause the video and then do the calculation. Okay, so if you did this correctly, you would have had 0.04 moles of both H plus and OH minus. And neither of them are in excess. They act they're equal number of moles. And this, everybody, here is the equivalence point. Okay. Because we say here that stoichiometrically equivalent moles of acids and bases have reacted with one another. And when I say stoichiometrically equivalent, I'm referring to the coefficients. the 1-to-1 ratio. So as long as this is also in the same 1-to-1 ratio, that would be considered stoichiometrically equivalent. It could be a 1-to-2 ratio, depending on whether it's a polyprotic acid. But when we say equivalent point, that's when the initial amounts match the coefficient 1/3 mole. Okay, so at this point in the beaker, okay, I'm going to ignore drawing water molecules. Okay, but we have here, okay, Na plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus. We don't have any H plus or OH minus ions because they've neutralized each other completely to form water. Again, Cl minus and Na plus have no effect on the pH, so the overall pH at this point is going to be 7. Okay, and that's because the amount of H plus and OH minus are equivalent, and they neutralize one another. Okay, so go ahead and try this now. See if you can make it all the way through, doing the before the reaction, the after the reaction, the molarity of the species left over, and the pH at that point. So go ahead and pause the video. So when you look here at my work, you can see at this point that all we have is OH minus. And so we calculate the molarity of the OH minus at the end, and we take the negative log of that to find the POH, which is 1.62, subtract that from 14 to get a pH of 12.38. Now, let's again draw the contents of the beaker so you can visualize what is happening. Okay, we have once more the Na plus Cl minus spectator ion, Na plus Cl minus, but now we also have the OH minus ion that can be impacting the pH. Okay, and OH minus is the only thing that impacts the pH, so the solution will be basic as a result in the end. So we're going to be talking a lot about this when we do the titration protocol, but you're going to be looking at a titration curve which talks about the pH, which graphs the pH over the quantity of base added up to that point. So in the beginning, the initial pH, in our example that we did, the pH started off very low, and it was 0. So because before you add any of the base, the pH is going to be very low because it's only acid at that point. So I would make a note right here that here it is the only acid present. So I'll put it on here to note that only acid present before any base has been added. Okay. Then in this part of the curve right here, okay, this is when the H plus predominate. Okay, so I'm going to make a note here that H plus is remaining. Okay, and it's only H plus. Okay, then the pH will still be less than 7 because only H plus is remaining, and that had the impact on the pH. Okay. Also notice that that slope is relatively flat. You're going to see in a little bit what it looks like when you add a strong base to a weak acid. But for now, you can notice that that has a relatively flat slope. Okay. Then we get to the equivalent point. And again, I want to make sure you take note of that terminology. Stoichiometrically equivalent at that point. And the pH is going to be 7 at that equivalent point because that's when the amount of H plus and the OH minus are equal, and there's nothing left to impact the pH at that point. Okay. That's the equivalent point right here. It is OH minus only. Okay, and if you have trouble visualizing, make sure you go back to the earlier slides and look at all of my drawing to see what I'm talking about. Okay, so you may want to take a break for a few moments, and then we're going to move on to the weak acid strong base calculation. So before we go into the calculations involving weak acids and strong bases, we also want to take a look at picking a indicator. And when you did the basic titration lab a few weeks ago, we used phenolphthalein for the color change to determine when you reach the equivalent point. And so what we do is we use an indicator that changes color somewhere near 7, but this is for a strong acid, strong base titration because the pH at the equivalent point is 7. And phenolphthalein is a good use for this one because it changes color on 8.3. And so that's a little bit past 7, but that's okay because you'll see from looking at the titration graph that the inflection point where it changes color, you can use to approximate the pH instead of knowing exactly where it changes color. And we'll take a look at that shortly. So calculations involving adding a strong base to a weak acid. Before we get started into this one here, make sure we emphasize again that a weak acid has a weak conjugate base. Okay, meaning that the conjugate base will have an impact on the pH. Okay, the strong acid has a negligible conjugate base, so that conjugate base will not affect the pH. Okay, so let's look at the calculations here. And we're going to first start with the titration of a weak acid with a strong base. Calculate the pH when 40 milliliters of acetic acid is first put into the beaker. You already learned how to do this in the last chapter, so go ahead and pause the video and work out the calculation. Okay, so if you did this correctly, you would have gotten a pH of 2.37. Note that when I had this drawing here of what the beaker looked like in the beginning, it is composed only of weak acid. Okay, you have not added any of the strong base NaOH at this point. So a visual representation of what that weak acid looks like at this point would be you have mostly HA with a tiny bit of H plus and A negative. A negative has an impact on the pH. So I'm going to go ahead and highlight that to emphasize that this is not negligible and this is not negligible. And those are going to be the main things that impact the pH. And the pH will be the negative log of the concentration of that H plus ion. And so that's what we use to do the calculation. Okay, and remember at this point, we don't have any strong base, so we do not need to do it before reaction after reaction table. Okay, so let's move on to the next one. Okay, calculate the pH when you've added 10 milliliters of 1 molar NaOH to the beaker. Now, the net ionic equation for what's happening right here. Okay, let's do the complete ionic equation first, which is, go ahead and fix that part. H C2H3O2 aqueous plus NaOH aqueous gives you NaC2H3O2 aqueous plus H2O. Okay, and you only break up strong acids, so we're going to keep this weak acid Hg2H3O2 together, and the Na will be spectator along with this Na. So the net ionic equation will be the Hg2H3O2. I'm going to simplify that to say Ha aqueous plus OH minus aqueous. It's not equilibrium because it's titration reaction go to completion. So C2H3O2 minus and water. Okay, so now we have a reaction happening. So let's go ahead and do the before reaction and after the reaction table. And in the earlier slide, we noted that we had 40 milliliters of the acid. So in terms of the number of moles, that is going to be 0.04 moles of the HA. And for the moles of the NaOH, we have 0.01 mole. And we don't have any of this, and we're not going to care about the water column. So clearly the limiting reactant is the OH minus. So using the 1-to-1 ratio, we'll know that we'll have only 0.03 moles of the HA, none of the OH minus, and 0.01 moles of the C2H3O2 negative. So at this point, I'm going to go ahead and draw the contents of the beaker so you know what is happening. And at this point, we still have the HC2H3O2. I'm going to again call that HA. HA. We started off, I think, with 6 earlier, so we'll make this like 4 of them. Okay, and then we had a little bit of ionization, H plus, and then we had the A negative, but now we have a little bit more A negative now. Okay, so again, the A negative has an effect on the pH along with the H plus. And this, my friends, is a buffer because you have both the weak acid, HA, and its weak conjugate base present. So that is the buffer at this point. So we could do an ice table, but because we have a buffer present, we can actually use Henderson-Hasselbalch's equation where the pH equals the pKa plus log the conjugate base over the acid concentration. Now, the beauty of Henderson-Hasselbalch is we do not need to convert the acid and its conjugate base to molarity. We can use moles because as long as the volume is the same, the ratio of the concentration will be the same as well. So to determine the pH at this point, that's negative log. The Ka value is 1.8 times 10 to the negative fifth, plus log the base is 0.01 over 0.03. And that gives me a pH of approximately 4.27. So when you look at the figure here, you can see that, again, the presence of the conjugate base will make the pH a little bit higher than it would be if it was a negligible conjugate base. Okay, think about that as we do the next one. You can use the same net ionic equation, but go ahead and see if we can do the before reaction, after reaction table as we're adding some more NaOH at this point. Okay, so pause the video and do the before reaction, after reaction table, and use the net ionic equation that we did in the last slide. So if you did this correctly, you had 0.04 moles of the HA, the analyte, and 0.04 moles of OH minus, which is the titrant. And you've reached the equivalent point because equal moles of the acid and the base have reacted. Now, what I want you to notice is that because it's the equivalent point, you're not going to have any of the weak acid or the NaOH at the end, and all of that will be been converted to only conjugate base. And the A negative is the weak conjugate base, like we keep emphasizing. So all of these A negatives in the end will have an effect on the pH. Okay, very, very important thing to note. In the strong acid, strong base, one that we did earlier, the Cl minus was the only thing present. So that was negligible and that had no effect on the pH, which is why the equivalent point was 7 in this one. In this case, because we only have conjugate base left over, this means the pH at the equivalent point is going to be greater than 7. So how do we determine the pH of that? Well, we know that the conjugate base will then undergo hydrolysis with the water molecule and undergoes the equilibrium, HA and OH minus. And we can do an ice table. And this is when we use the molarity of the conjugate base, that's from earlier right here. And that was 0.5 molar water. Okay, we had no HA and OH minus until the A negative undergoes hydrolysis. We're going to go 0.05 minus X, which is, roughly 0.5. And then this is plus X, X and X. So since this is the conjugate base, we can say Kb equals HA OH minus over A negative. Okay, so how do we come up with the value of Kb? Well, Ka for this is 1.8 times 10 to the negative 5. So the Kb for the conjugate base will be 1 times 10 to the negative 14th divided by the Ka of that 1.8 times 10 to the negative 5. And we can put that in the calculator, and I end up getting 5.56 times 10 to the negative 10th power. And going to plug that into the Kb expression. Okay, x and x is x squared, and A is 0.5. Okay, and I will solve for x in this case, and x is approximately equivalent to 1.67 times 10 to the negative 5. Okay, and that's going to be the concentration of specifically hydroxide right here. So we can find the pOH first by taking the negative log of that number. And I'm going to go ahead and just do that part right here. 4.78. So the pH at that equivalent point would be 9.22. And that goes back to what I was saying earlier. At the equivalent point for a strong base, weak acid, the pH will be greater than 7. You cannot say on the AP exam that the equivalent point of a weak acid strong base titration is greater than 7 because something like the strong base wins out. It's because the conjugate base of the weak acid is the only thing present of note at the equivalent point, and that weak base will undergo hydrolysis with the water molecule to produce a hydroxide ion, which therefore give a pH greater than 7. So you have to really be able to explain what is happening at the molecular level to discuss, to provide a reasoning and justification for the phenomenon that you see. All right, so there's still more, folks. Go ahead and do the BR, AR, and also do the molarity at this point, considering what the volume of the solution is. So look at what we did here. If you did this correctly, you would have seen that this time the weak acid HA was the limiting reactant, and the strong base OH minus is excess reactant. If you look at the content of the beaker that I drew on the right side, you're going to see that it contains a negative ion as well as OH minus ion. So at this point, we have both a weak base, really the conjugate base, as well as a strong base present. Okay, so before you start freaking out about having to do another equation, another calculation, what you should know is that when you have this scenario, the only thing that really matters here is the OH minus concentration. It has a much greater effect on the pH than the weak base does. So all we have to do to calculate the pH at this point is to first calculate the pOH, which is negative log of the hydroxide concentration, okay, which was 0.024. Okay, and you take the negative log of that, 0.024, I get a pH of 1.6, pOH of 1.62. So the pH is approximately 14 minus that, 12.38. And that concludes the titration. Couple of things I do want you to know is if you look at a titration curve of a weak base and weak acid, strong base, the pH starts off a little bit higher, okay, than it would under a strong acid, strong base titration. The pH is going to jump up initially, and then it's going to flatten out because this is the buffer region. And then it's going to hit the equivalent point, and then it'll go up this way with the strong base. Okay, and the buffer region, okay, is when the weak acid and its conjugate base is present. So that would be here like the buffer region. Okay, and the pH at the equivalent point right here is going to be greater than 7. Okay. For a strong acid, strong base titration, the pH will start out very low, and it's still flat, then it jumps up, and then it flattens out again. And that pH would equal 7 at the equivalent point. And that's for a strong acid, strong base titration. Note that that does not create a buffer because you have to have a weak acid and this weak conjugate base present, which is not the case when you only have a strong acid, strong base titration. And that's something that people forget. Now, one word of warning, you've got to be careful because so far, and actually in this case, we've only dealt with adding a strong base to a strong acid and adding a strong base to a weak acid. But you also need to know what the curve looks like if I flipped it and you add a strong acid to a strong base or adding a strong acid to a weak base. We won't be doing any calculations involving the titration of a weak acid and a weak base because that gets really complicated and messy. But you do need to know all these different scenarios and what's happening at each point in the scenario and what the curve looks like. Okay, you also, when you do the POGL, the titration POGL we're doing, I also want you to take quick notice of the half equivalent point. Okay, I'm going to write that down for you, the half equivalent point. And I'm not going to go over this part in lecture, but I'm hoping that you guys can see what's so special about that region, and that would be when you get halfway to the equivalent point volume-wise. So I know there's a lot to take in. The titration POGL will hopefully illuminate some more of this for you. I tried to add clarifying details as much as I could, but there's only so much I can do in this lecture. And last bit, make sure you know what buffer capacity is. Buffer capacity is the how much of a added strong base or strong acid that a buffer can take on before the pH changes dramatically. And know that the pH of a buffer solution, we mentioned this earlier, is given by the formula pKa plus the log of the A negative, and HA. And if you want a solution with, like, say, a pH, a buffer solution with, say, a pH of, say, 5.7, you're going to want to pick an acid with a pKa that's closest to 5.7. And hopefully from the preparation of a buffer lab, you can understand why that is the case. But that is something that's very, very important. So good luck with absorbing all of this, and definitely take your time when you're doing the titration protocol, because that can be really, really helpful in getting you through all the material.